So this weekend coming up, the 30th of October, the night before Halloween, the Sierra College Natural History Museum will have a free first Saturday. So before the pandemic and now kind of hopefully tail end of the pandemic, we'll have these free first Saturdays where usually younger kids and their parents come in and visit the museum. And this is a fun one. We're doing a night at the museum.
People out the candle.
Nick and I will be volunteering for that one. And today I'll go over the announcements and then we'll continue with chapter 5 and more about this.
Hey, and the amount of time professors can put into.
Someone asked.
Is that your professor for Kim?
I feel like I know him.
Not muted.
He looks so familiar.
Really?
Can you mute? All right. Okay, I think we're good. Thanks. All right, so maybe one of my former students there, who knows? So night at the museum. If you or a family member want to attend, it might be tough. They only have 350 reservations. And when I checked on Friday, there was only 8 spots left of the 350. So it might be sold out already, but you could still attend if you want to volunteer. So Nick and I, and then 2 of his friends, high school friends, you can see the Whitney High freshmen are volunteering. And if you want to volunteer, I'll give you 2 points extra credit. And they encourage us to wear costumes. And I think the kids come, they're wearing costumes. Could be fun, right? And then the details of it are, it's this Saturday coming up, and you'll help out at one of the booths, like setup or like treat bag stuffers, exploding pumpkin assistant. That sounds fun. Skull and pumpkin bracelet instructors, crafts and things. So if you're interested, you should email Rachel, the museum director, Rachel. Here's her email address. Put Boo as the title and then just say I'd like to volunteer, and she'll get back to you, and you can volunteer free for Saturday. And then you can come to do lab work early as always, but today it's a little different, today and tomorrow, because Monday, Tuesday we have the exam. So don't come early don't come early for the lab work, because people can come early for the exams. But on Wednesday and Thursday that applies. And exam 1 today and tomorrow in lab. So I've told you this a couple times already. I'll just get to the main points. So Monday lab students, you can come early today at 1 p.m. if you want to start early instead of your 2 p.m. start time. And then Tuesday students can come in at 9:45 instead of the normal 10:45 if you want, coming out earlier. And then the Tuesday 2 p.m. people, you can come in out early to 1 p.m. And when you come in early, just come in quietly if someone's already taken the exam. And then place your cell phones at the front of the class and start the exam, no notes. Yep, come quietly. And then after most people are done with the exam, if I have a couple or a few people finishing up, they can come into my office and finish up, and others can do lab work. So we might as well take advantage of the lab time while we got it. And prepare for lab. Maybe you're not focused so much on preparing for lab tonight if you're taking the exam tomorrow or today, but that's okay, because just focus on the exam. But after the exam, prepare for the Wednesday, Thursday lab so you can come in, get a lot done. And I'm updating the next lab assignment, chromatography. I'll get that out to you soon. So that's the one that's going to follow extractions. And I will have my office hour as normal tomorrow, but I won't be able to, if someone says, oh, can you tell me how to do a problem that was on the exam on Monday? Because I'm taking it Tuesday. That won't be good. I won't do anything like that. But come and ask questions and get help still. This Wednesday, Thursday in lab, we'll start working on the Stereochem Workshop. I posted that and I'll print it up for those of you who want it. It's not a long workshop. It's much shorter than the other ones. And it's just for us to spend a little time using our models and really getting the idea of this Stereochem. And I posted homework 5 as homework D, chapter 5 as well. That's Stereochem also. And I'll set the due date when we finish it in lecture, the Stereochem chapter 5. And that's it. Any questions about the intro? Okay. So let's get going then. So we started talking about stereochemistry. And we talked about isomers and the different types of isomers, constitutional and stereoisomers. Let's do a really quick review on that. My Jamboard here. Okay, so I'll make a little thing first to fill in here. So let's say same molecular formula. What does that apply to? And then same connectivity. What does that apply to? And then mirror images. What does that apply to? So for these guys, just isomers in general. Which one of these does this apply to? Could I say, what should I say? Same connectivity, mirror images, same molecular formula. It's kind of a funky question because isomers applies to both stereo and constitutional. I had a question on the chat about spectroscopy. I can help you a little bit on that. Let me just finish this real quick review here. So what do you think? Isomers, how should I associate isomers with these criteria? Do they have the same molecular formula? Yeah, I see it there. Same molecular formula. What about constitutional isomers or structural isomers? Okay. Make it a little smaller. So the constitutional isomers, same molecular formula, but not same connectivity. So it's just that one. And then stereoisomers. How are they? What applies to them? Same molecular formula because they're isomers. And same connectivity. Now, mirror images, we don't know enough yet, but we're going to get to it now. So, and then let's go diastereomers first. Diastereomers. So diastereomers, do they have the same molecular formula? Yep. Do they have the same connectivity? Yep. Are they mirror images of each other? No. Okay, finally, enantiomers. Enantiomers. I think that's right, spelled right. Enantiomers. Yep. Okay, enantiomers. So, same molecular formula? Yep. Same connectivity? That's right. And are they mirror images to each other? Yes. Okay. Oh, I didn't put different three-dimensional arrangement, huh? I'll add that down in here. So enantiomers, different three-dimensional arrangement, same with diastereomers and stereoisomers in general. Okay. All right, so now I'm going to, I'll do that problem you were asking about real quick here. So there was a question about the spectroscopy on homework C, chapters 3 and 4. Let's do this one real quick. Trying to move all my stuff, all my Zoom chats and all right, so one of the keys of this that I see a lot of students not using, it's not like something that's pretty easy to do with spectroscopy, but the students aren't doing it, you're not giving yourself this advantage, is looking at the integration. So if we have 11 total hydrogens, right? Then we can look at the integration and figure out a ratio. So let's say I said this was 1 hydrogen, then this one looks kind of like 3. It doesn't look like double to me. Doesn't look the height of the integral. And if that's 3, then this is 6. Does that add up to 11? Oh, you know what? It's not 1 to 3. I'm sorry. I meant, I'm messing this up. If that's 1, then this one would be 1.5. I think it doesn't look like double. And then if that's 1.5, this one will be 3. But that adds up to 4, 5.5. Oh, that's half of 11. So if I just double everything, if I say this is 6, that's 2, and that's 3, then we're good. So when I have a, oops. If I have a 6 hydrogen singlet right here, what does 6 hydrogen singlet suggest? Whenever you see 3 hydrogen singlets, you think methyl, right? That should be your first guess. Yes. But if I have a 6 hydrogen whatever, I should think 2 methyls are equivalent. So they're like this. 6 hydrogen signal like that, right? Also, that's symmetry in the molecule. Also, if I look at my carbon signals, I see I have 1, 2, 3, 4, 5 carbon signals, and there's only 6 carbons, 5 total carbon signals, but 6 carbons in the molecule. In the molecular formula. So that means there's symmetry too. All right, and then the other thing I look at is I see over here, oh, look at this, I got a quartet and a triplet. What does that suggest? That suggests ethyl. Remember, ethyl has 2 hydrogen quartet, 3 hydrogen triplet. And I have a carbonyl, obviously. And my carbonyl, it's carbon signal, it's less than 200. So it's a carbonyl with resonance. So, and I've got 2 oxygens in the molecule. Is it looking like it could be like a carboxylic acid maybe, or an ester? But I know it's not a carboxylic acid. How do I know it's not a carboxylic acid? Yeah, carboxylic acid has a big mess here for the OH of the acid. And if I have an acid too, there'd be a signal around 12 in the proton NMR. It's not an acid, it looks like an ester. So I'll just start drawing out the basics of an ester. Here's an ester. It's got a carbon and another carbon, right? And then I know I need like a 6 hydrogen singlet, you know, this one here, right? This sort of thing, and an ethyl. So I can try this either way. Let's say I go ethyl here, and then a 6 hydrogens singlet. Well, that wouldn't be a singlet yet, but say I went with that. Then I could say, oh, did I use up all my carbons? I need 6 carbons. 1, 2, 3, 4, 5, 6. Yeah, that looks pretty good. This almost looks good, but right now this is a 6 hydrogen doublet, huh? How can I get rid of, it has this neighbor. That neighbor's messing me up. Oh wait, I haven't used my chlorine yet. Maybe I'll put the chlorine right here. Oh, that would take care of the coupling, huh? Now I will have a 6 hydrogen singlet, right? That I need. But does everything look right? Let's check. So this right here would be a 2 hydrogen quartet, and it would show up approximately where? Alpha to an oxygen, about 4 parts per million. Uh-oh, it's not looking right. Uh-oh, what can I do? Something's wrong here. I put the ethyl on the right side on the oxygen, and I put this isopropyl on the left. What if I switch these two? Let me try that. Let's go. Put the chlorine down here. Aha. That's looking better now because I can say two hydrogen quartet around 2 parts per million. And that's looking like more like what we got, huh? You can figure out the rest from here. Correct. This one's wrong. It's pretty close though. If you answered this one on an exam question, this was an exam question, I would give you like most of the points. You know, you're pretty close. That helped the strategy. I'll do this one really quick too. I think many of you might be struggling with these because you don't know your values well enough and you're not using integration. So practice those values and know like quickly like, oh, in this one I should see right away. Oh, it's a benzene ring. It's an aromatic ring. And on this one, it's all about the integration is going to really help you. When I'm grading the homework assignments that had this, a lot of people gave me this answer, an answer with a monosubstituted benzene. So a monosubstituted benzene has 2 carbon signals here, 2 more here, and 1 there. So 5 hydrogens that are in the aromatic region. Do we have that on our thing? Let's look. There's 10 carbons total. 10 hydrogens total. How do I divide these up? I'm going to call this one 1 over here. that looks like 1 in the short one. And if that's 1, this looks like 2, that looks like 2, this looks like 2, and that looks like 3. Let's see, does that add up to 10? 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that looks good. So this means I don't have a mono-substituted benzene. I have a di-substituted benzene. I gave you a homework, extra credit assignment last week. Do it if you can. Practice it because it'll help to know this kind of thing, you know. Okay, and then so if I got that, that means I have a di-substituted benzene could be XY like that. XY like this, or XY all the way across. We'll talk a lot about these in the future. This is the ortho, meta, and para. You don't need to know the ortho, meta, para terms yet, but you should understand that's a possibility. And it looks like I've got a nice doublet and another doublet, huh? That's classic para substituted. Para di-substituted benzene. So this would be a 2 hydrogen doublet, and this would be a 2 hydrogen doublet. So you got that for sure. And in terms of carbon signals, we should have in the aromatic region 1, 2, 3, 4 carbon signals. It looks like we do. Yeah, there's 4 aromatic carbon signals. It's symmetric, right? Okay, and degrees of unsaturation, it's going to be 9 plus 1 minus 10 plus 0 minus 0 over 2. It's going to be 10 minus 5 is 5 degrees of unsaturation. So we've already got 4 of those degrees of unsaturation in 1, 2, 3, 4 in the benzene ring, right? 1, 2, 3, 4. And we see a carbonyl here. And the carbonyl carbon is over 190. It's looking like a ketone. Yeah, oh no, it's an aldehyde right here, aldehyde for sure. So let's throw an aldehyde on one end of this guy. Then we need something over here. And we've used up the oxygen. Ooh, it looks like what here? What does this look like? A quartet and a triplet. Ethyl, huh? So I can put an ethyl there. Does that give me all my carbons? 9 carbons, 6, 7, 8, 9. Yes. Yeah, and this is my 2 hydrogen quartet, 3 hydrogen triplet. Yeah, it's looking good. Doublet. Oh, that's the molecule. Okay, so hope that helps. Back to lecture on stereochem. So let's work on these chiral centers, how to identify them and name them, and assign their absolute configuration, the R and S. So I'll just make up a bunch of examples of that stuff. So the molecule I just drew up, how many stereocenters does it have? And remember, a stereocenter is a tetrahedron with 4 different groups. So is this one a stereocenter? Is this carbon a tetrahedron? The one with the fluorine. So this is a tetrahedron. It has a hydrogen that's wedged out on it, right? It's got 4 different groups on it. So that's a tetrahedron. And does that tetrahedron have 4 different things on it? It has a hydrogen, a fluorine, a carbon, and a carbon. It's kind of looking the same, but then as I go a little further, I see, oh wait, this has 2 hydrogens and a carbon, where this carbon here has 2 carbons and 1 hydrogen. So they are different. So this is definitely a stereocenter. I'll put a little asterisk by it to emphasize it if I can get my blue to turn on. There it is. Okay, so that's a stereocenter. Tetrahedral, 4 different groups. What about this guy? Is this one a stereocenter? Is it tetrahedral? It is tetrahedral for sure. Got 4 different things on it. Does it have 4 different groups attached to it? No, because it has a methyl here and a methyl here. Those are 2 things that are exactly the same. Not a stereocenter. Not a stereocenter. So, okay, we just have 1 stereocenter to deal with in this one. Let's do it. And also, I could have drawn this problem up in a way that wouldn't have confused you. This confuses students a lot. I don't want it to confuse you on the exam, and I'm giving you examples of it now on the homework in the Stereochem Workshop. And there was some other place, I don't know, probably in exit questions. So try not to get tricked by this. So if I would have drawn the problem up differently, though, if I would have went like this and just drawn it without the wedge, I think you would have been less likely to get fooled by it. It is completely fine to draw this wedged, and it's also fine not to draw it wedged because it's not a stereocenter. I don't have to tell you whether it's wedged or dashed because it's rotating itself. It doesn't matter. Okay, but then let's go back to our stereocenter we do have. So what is the highest priority group on this stereocenter? Is it the fluorine, the hydrogen, the carbon here, the carbon there? So when we do these priorities, we look for the atom with the most protons. So who has most protons? Hydrogen. In terms of protons, I'll write protons in blue. Hydrogen has 1 proton. Fluorine, let's see, it's 9, right? The carbon that's right here, this carbon has 12 most often. We do know about carbon 13, but we're going to go with, the most abundant isotope. Okay, so who's the highest priority? Fluorine's the highest priority group here. And now before I decide between this carbon and that carbon, let's look at this H1 and know that, oh, that's going to be the lowest priority. That's going to be our D. That's what we're going to use to orient ourselves to visualize this correctly. Now carbon 12 and carbon 12, we're tied up here. Do we just stop and say, oh, it's a tie? No, we got to keep going. Got to just continue on down the line. So let's go. And I'm going to make the next things in color. So after they're tied at carbon 12, then I have another carbon, and a hydrogen off of this one. That's it. It's step 2. And then this guy has got 2 hydrogens and a carbon. So what you do, it seems you probably already know the higher priority. Is it the right one or the left one? Who's higher priority? Yeah, it's the right side. That's higher priority. But the proper way to do this, that'll make sure you don't make mistakes with more complicated ones, is to think of it this way. Whatever's on this carbon on the right, you take its champion. So its champion currently is either of these 2 carbons. I'll just choose this one. So this champion is going to battle the other side's champion. So here's the champion over here. So initially the 2 champions battle, stalemate. Then I have to go to the next champion. So for the right one, this is the next champion, and it has to battle the next champion, which is one of these hydrogens. So this will beat that at that point. Okay, so that means that the right side is priority C and the left is, no, this one's B. This is B, and this is C. Got it. Okay. So are we viewing this correctly? Do we have the D facing away from us? No. So I'm going to teach you many ways to deal with this situation where D is not dashed away from you. The most fundamental, like best big brain way to do it is try to visualize yourself behind the molecule. So if you visualize yourself behind the molecule, if you could put yourself in the screen, like go into the matrix, get behind the molecule, then D would be facing away from you. Fluorine would be down. The B would be, for you, it would be on your left. A, B, C. This is going to go clockwise. So from correct view, the arc from A to B to C, that's what we do with A and B and C. It's going to be clockwise from the correct view. And so this molecule is R. If you don't know that you need to use the D to visualize it, you might say, oh, look, it's counterclockwise right now, but we're viewing from the wrong side. And you might say, oh, it's counterclockwise. It's left-handed, it's sinister, it's backwards. All lefties are bad. Just kidding. So if it's, you could call it S, but it's not, it's R. Okay, so this trend that if your lowest priority is wedged out at you, whatever you see from this side is going to be the opposite on the other side. That totally applies when the D is wedged. If the D is in the plane of the page, then it doesn't. So try to be careful when you're learning about this. Students, a lot of times, they want to make up rules for things, and they don't really, they're just looking at a trend, they're not understanding it, and they'll make up a rule that doesn't really work. But there is one rule here where it does work, where if your D is wedged, you're just, whatever you see from this side, the priority is the opposite. Okay, let's do some more. The best thing to do with these is just practice. And to know that I want you to make mistakes with this, because if you make mistakes now, it's better than making them later. Let's look at this one. Ooh, I'm going to do this right. Present from current slide. I got it. Okay, a chiral, a molecule that will blank. Have I talked to you about the plane polarized light yet? I forget if I talked about that. Okay, I'm going back. Okay, there's this thing called a polarimeter. This is a polarimeter. And a polarimeter, it's one of the earliest pieces of equipment that chemists had. We had chemists use polarimeters before NMR, before IR, but it seems kind of fancier to me in a way, but it's not, it's older instrument that's been used for a long time. And the way a polarimeter works is you have some light source. It's normally, the most common is a sodium light bulb, kind of like you see in big cities. You'll see in Oakland and other areas, like yellow light under a bridge at night or whatever. You see that yellow light, it's a sodium lamp. So we have this sodium lamp, and think of it as a beam of light that comes out in like a column. So it's got all these waves oscillating in all planes. And then we put it through a polarizing filter in the instrument. It has a polarizing filter. And this filter is like a big deal. It's what's it called? It's Iceland spar. Because I guess it was found in Iceland, and then sailors use it to help navigate this Iceland spar. But anyways, what this polarizing filter does, it takes this column of light, you can think of it, and puts it into a single plane. So it's just a plane of light, and it can come out, straight up and down like this. So say that plane of light comes out straight up and down. Then if you have a molecule that's chiral, something with the stereo center like this one. So this is chiral, this is a stereo center. It's got a tetrahedral carbon and 4 different groups. And when it goes through a solution of a with chiral molecules, the plane of the polarized light gets rotated a certain number of degrees, depending on the molecule. So this one, it looks like it's being rotated counterclockwise, maybe by 30 degrees. And then the instrument, you read the value here. So the enantiomers we were talking about at the very beginning, they're very similar, right? They have the same molecular formula, enantiomers, they have the same connectivity, same different three-dimensional arrangement, but they're mirror images of each other. So enantiomers are so alike, if you just throw one up, like a model of one on the counter and a model of another one on the counter, it's hard to tell which is which. But when you put them in a polarimeter, one enantiomer will rotate the plane polarized light clockwise a certain amount. It might be like 15 degrees clockwise. The other enantiomer will rotate it 15 degrees counterclockwise. For you, was that clockwise and counterclockwise? Whatever. So enantiomers, you can tell them apart with a polarimeter. That's been a big help in the world of organic chemistry discoveries. Back in the old days, the chemists like Louis Pasteur, they used a polarimeter to determine enantiomers for the first time, and to then figure out the structure of a lot of our important sugars or carbohydrates like glucose and fructose. They used polarimeters before there was such things as IRs and NMRs. They had melting points and polarimeters back in the day, and they super bright, worked hard and figured out a lot. Okay, so that's a polarimeter. We have a polarimeter and we may use it next semester. We won't use it this semester. Depends on where I'm at with labs. Okay, so a chiral molecule. Chiral, it actually refers to handedness, like your right hand and your left hand, and we'll see. You can see like if I hold up my right hand in a mirror, if this is a mirror, my left hand is a mirror image, like my thumbs match up, but they're not the same hands, because when I try to like put them over on top of each other, if I have both hands facing up and I put them on top of each other, thumbs don't match. So hands are chiral molecules that are mirror images. Enantiomers are chiral. So chiral molecules that will blank plane polarized light in a polarimeter. What's the answer there? Rotate. Yeah. So any solution or molecule you put in a polarimeter, if it rotates the light, it's chiral. If it doesn't rotate it, if it comes in at 0 degrees, comes out 0 degrees, then that's an achiral solution. And then how do you predict a molecule is chiral without a polarimeter? It's not the same as its mirror image. So enantiomers are chiral. Anything that when you make it, you have a molecule, you make its mirror image. If it's a different molecule, it's chiral. And chiral centers or asymmetric centers, or I usually say stereocenters, are tetrahedral atoms in a molecule that has blank groups attached to it. Are the groups all the same or all different for a chiral stereocenter, chiral center or stereocenter? They're all 4 different groups. Okay, so now let's do this one. Okay, so I'm going to start off with this upper left molecule with the alcohol and the fluorine. Does that molecule have a stereocenter? This one right here. Is there a stereocenter for this molecule? Yes, it does. Is hopefully you're seeing this is the stereocenter right there. Is this a stereocenter? Is this tetrahedron a stereocenter right here? Is that a stereocenter? It's tetrahedral, right? No, because it's got three of the same hydrogens. not a stereocenter, abbreviated. Okay. Okay, but we do have one stereocenter here. So let's prioritize. Who should be the highest priority? The oxygen, the fluorine, the carbon, or the hydrogen? So remember, fluorine's in group, it has not group, it's got 9 protons. Oxygen has 6. So fluorine's higher priority. Fluorine's A. Who's the second highest priority? Oxygen. Good. And then the third highest priority? The carbon. Yep. Because carbon's in, how many protons does carbon have? 4? Oh, wait, no. Oxygen has 8. What am I doing? Carbon has 6. So carbon is that, hydrogen has 1, so it's the lowest priority. Okay, so we've got our priorities straight. Got to get your priorities straight. Make something of yourself. And after you've got your priorities straight, then we use D, the lowest priority, for what? D is to orient the molecule to make sure we're viewing it properly. So is D in a good spot here? Is D pointing away from us? It's an easy one because it's pointed away from us on this one, huh? So once I've got myself oriented where I'm looking at the molecule with D pointing away from me, then I just draw my arc with the other letters. So D is done, its job is done, I've already set up. And now the A, B, and C, they're the arc. I don't draw the arc all the way around to D, I just go A, B, C. So that arc, I'm viewing it correctly. Is it clockwise or counterclockwise? This is clockwise. And you can easily make a mistake with this. I think whenever if on an exam, like on exam 3 and 4 or 5, you know, the rest of them for the year and next year. So whenever I do a determination, oh, this is clockwise, I like to kind of look away, look at the clock if there's one in the room and see if I'm right. Like, does that make sense? Let me see. It's 12 o'clock here. 1, 2, 3, 4, 5, 6. Yeah, that's clockwise. Because for whatever reason, my brain will mix this up all the time, and most of you probably are the same. So just double check yourself. Once you have that it is clockwise and you're confident you're right with that, then assign it. Clockwise is R or S? Which one is it? Oh, you know what? I drew the arc backwards, huh? Thank you for helping me, Annalise. What did I do? The arc should go from A to B to C. See, I'm telling you, I make mistakes on this. So this arc now, is it still clockwise? Sorry. So A to B to C, is this clockwise or counterclockwise? This one is counterclockwise. Yeah. And so if it's counterclockwise, is it R or S? S. Yep, it's S because back in the day, people thought if you're left-handed, you're sinister, you're different. Different is wrong. And so counterclockwise is considered different. But now we know, let's look at the World Series rosters, and they're almost all lefties. And I think parrots, they're left clawed more often than right clawed. And I don't know how they figure that out. Maybe they hand them something. Would it be the claw they grab the thing with, or the thing they stand up with that's their stronger one? I don't know. Okay, so we got S. Now let's look at our next one. Is this molecule, does it have a stereocenter? I've got is this carbon right here a tetrahedron? The one on the bottom right? That is a tetrahedron. Is it have 4 different groups? No. 3 hydrogens is exactly the same. Not a stereocenter. Is this a stereocenter? No. What about the middle one? This looks like a stereocenter. Is that a stereocenter? Oh, good. I'm getting a lot of no's on that one. So this one's not a stereocenter. Has two methyls that are exactly the same. I guess I could have drawn it like if it was drawn, let's see, H. Not in with wedge and dash, you'd say, oh yeah, that's not stereocenter. Okay, let's move down to this one. So is this a stereocenter right here? It's got a chlorine, a carbon, and a carbon that's an alkene. What do you think? Is this a stereocenter? Tetrahedral? No. Trigonal planar. Not a stereocenter. All right. So we have to have tetrahedrons. We have other tetrahedrons in the molecule, though. This is a tetrahedron. Is that a stereocenter? No, that one has two hydrogens that are exactly the same. Not a stereocenter. But I'm hoping you can see this one is a stereocenter right here, huh? Okay, so I'm gonna zoom in on this one. I'm gonna go color code my like steps. You have to figure these out in steps, like slowly. So initially for this stereocenter, I have a carbon here. That's like step one. I'm gonna do it in green, and I'll make this one green too. I got a carbon there, oxygen here, carbon here. So do I have any assignments I can make yet? Do I know who's the highest priority, lowest priority, anything like that? That's step one. It's step one in green down here. I think I can assign a priority at this point. Which priority can I assign? Oxygen, it's the highest priority A. That one's done. I know that's the highest priority. I don't have to go down the oxygen to the hydrogen. You just, once you have a difference in the groups, you just assign whatever you can assign. You don't keep going. But let me show you now the next step. So for, oops. So for the next step, it's going to be this carbon that's attached to that, and then the two hydrogens. And then this one has got two hydrogens, right? And another carbon. And then this bottom one has two hydrogens and another carbon. Okay, so let's see how we do this. They're all tied at this point, huh? Like the champion carbon battles this champion carbon, the other tied. Wait, I want to erase that. Yeah. That got confusing, sorry. Oh no, I did need that there. Yeah, that's right. So it looks like it's tied still. Got to keep going. Let's change colors. Let's go red. Over here, I've got three hydrogens. That's my third step. Okay, so let me actually do this. Blue was second step. Step two in blue. Step three in red. Okay. So over to the wedged out group, which started wedged. It's got three hydrogens at step three. What do we have for step three over here on the right? I've got a chlorine and then a carbon. And we actually count that as two carbons when it's a double bond. For this one, it's got a chlorine, it's got two hydrogens and that same carbon. They share that right there. So I have differences now. I can assign my next set of priorities. So I've already established that the oxygen, it was already one when it was oxygen, it was done. And now who's going to be the second highest priority? Who's B? It's going to be here, right? Because it led to the chlorine. This chlorine is going to beat out the carbon on this one. It's going to beat out the hydrogens over there. So that's definitely B. And then what's C? C is going to be right there because it has 2 hydrogens and a carbon, which beats out 3 hydrogens. And finally, this is my lowest priority, D. Okay, so this thing kind of got crazy. There's a lot going on with this one. Let me just redraw it with only the priorities. So I'll go like this. So highest priority is the dashed out oxygen in the back. Then we've got B over here, C here, and D there. All right. Are we viewing this correctly? Is the D pointing away from us? It's not, huh? D is coming at us. So we have to visualize it from behind the screen. So I'm going to show you tricks that don't require you to visualize behind the screen, but I believe you're better off learning how to visualize it from behind the screen. Try to get good at that. So if we're visualizing it from behind the screen, then our arc, our A to B to C arc, is going to look opposite of what we're looking at now. It's going to be counterclockwise. And so this is going to be S. I'm double checking because I always make mistakes on these. Okay, this next one. Is this a stereocenter? Is this a stereocenter? No, it's not a stereocenter because it's as you step around, it's like, oh, I'm the same, and then they meet. So not a stereocenter, no RRS for that. And if you think about it, let's say I was confused for a minute and I thought it was a stereocenter, then I would say, okay, they're tied. Okay, they're tied. Wait, I can't decide who's higher priority because they meet up at the same spot. And then this last one, let's do on the next panel because this one has multiple stereocenters and it's all right. So how many stereocenters does this one have? Let's see. We got 1 here, 2 there, 3, 4 stereocenters. I'll just start with the top one. I'll put the H here. I know that one is my lowest priority for sure because it's, it's a hydrogen versus carbon, carbon, carbon. And I can see that this one's going to be this is going to be my second lowest because it's got 3 hydrogens on it, right? That's going to lose to this one's hydrogen, hydrogen, carbon because the carbon will beat it out. And this one's hydrogen, hydrogen, carbon. So yeah, hopefully you're starting to see the trend there. And then which is going to win out? If I go down this side, if I go to the amine, they're the same when they both go that way. But as they go outside, they get different. So as I go outside, I'll have a CH2, CH2, CH3. Here I'll have a CH2, CH with 2 carbons. This is going to win. So this will be my A priority. And this will be my B. And it has to do with the step right here. So at this point, they both have carbon. They'd be tied at that point, right? This carbon would have 3 hydrogens and a carbon, where this one I'll have 2 carbons and a hydrogen. So that wins out with the 2 carbons. Okay, is our D pointing away from us? No, not pointing away from us. But we can still draw our arc, A, B, C, and visualize it. As from the back side, it's not going to be this, what it looks like right here, which is, looks counterclockwise. It's clockwise from the back though. So this stereocenter is R. Okay, I had to write on that one a lot. Let me do this. I'll bring it. I'm going to copy the thing over again to another panel. And let's work on this right one here. So this one we determined was R. Let's work on this one next. So initially, I've got a hydrogen wedged out, a carbon, a carbon, a carbon. We're all tied at that point. But then this carbon goes to a nitrogen, which is going to beat out all the rest of the atoms, the carbons and nitrogens and everything. So I can see this is going to be A. Whereas here, I've got a CH2, CH2, and then I got another CH2, then I've got a carbon with 2 carbons and a hydrogen. So that's going to be my B. This is going to be my C, and then the hydrogen's going to be D. It's pointing at us again. A, B, C, looking clockwise, but from behind, it's counterclockwise. So this one is S. This one's a challenging one. This will be a great one to practice later after we've done more. You'll get good at it. At first, it's tougher than you think it's going to be in the long run. Just practice. So now this one we had, I think we went R and S already, huh? Double check R and S. Yeah. So now for this one, the first step is easy to tell because it's nitrogen versus carbon, carbon, hydrogen, which I'm assuming you all can already see that's the lowest priority, huh? Okay, so for those 2 carbons, they're going to do the same thing going up here. So I don't have to worry about that. But when I go to the right, I get a CH2, 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 C with 2 carbons. Yeah, that's going to be your B. B, C. So we draw our arc, A to B to C. And I'm viewing it from the wrong way. So it's not clockwise on the other side. It's counterclockwise on the other side. So this one is S. Let me double check myself there. A, B, C. Yeah, that's going to be counterclockwise. All right, one more on this one, and then we'll take a break. This last stereocenter is right here. And should be obvious by now that this is our lowest priority, D, the hydrogen coming out at us. And then our first steps are carbon, carbon, carbon tied. But this one is definitely going to be the A priority because it gets to that nitrogen right away. Whereas now the next one's going to be, I got to double check here to make sure. This is an H, this is an H, this is a C. H, H, C. They're still tied. This one has a hydrogen, a carbon, and a carbon. This one has a carbon, carbon, hydrogen. They're tied still. Whew, this one's a tough one. Now I've got to go the next step down. I got 3 hydrogens here, 3 hydrogens there. And then this one's gonna have 3 hydrogens here, 2 hydrogens here, ooh, and a carbon. So this one carbon champion is gonna take out all those other hydrogens. So that's gonna be our next priority. This is gonna be B, and this is gonna then be C. So let me draw my arc, A to B to C. It's looking counterclockwise, but from the other way, it's going to be clockwise. So clockwise, this one is R. Let's double check. I wonder if this molecule will not be too big to where I can draw it on Marvin's sketch and get the get it to name it for me. Oh, that's too much. Go. NH2. I think it might. There we go. Yeah. So let's say we got 1s2r. Copy this over. Huh. My text box, there it is. So the numbering is such that the methyl is 4. The methyls, this is carbon 4 of the ring. And then on the second carbon, we got the 2 methyl. This is carbon 2 then, huh? So you know they're numbering from the nitrogen. 1, 2, 3, 4, 5, 6. So 1 is S. Is that what we got? No, I got R. Uh-oh. Wait, no, 1 is S. Sorry. What did I get for S? I got S. Yep, I got 1S here. And then 2 is R. So this is 2, it's R. That's what we just got last one, yep. And then 4 up here is R. I believe that's what we got as well. Yep. And 6 is S. And did we get S for 6? We did. So we agree with Marvin's sketch. Okay, so if that was a little bit like hazy, like whoa, we're gonna practice more, and we have that Stereochem workshop that'll help too. But the key is just to practice these. If you, and then I joke a lot of times saying like when you're first doing these, I want you to make mistakes, because if you don't, you get this false sense of security, like, oh, this stuff's easy, and then you'll make your first mistakes on the exam. So we'll practice them and get good at it. Got another problem from our lecture outline. This one is meant to help you see how we should go stepwise through our assignment of priorities. So, okay, now it showed up good. So for this one, let's go stepwise. So step 1, I have a hydrogen here. Oh, what am I doing? It's dashed back, huh, the hydrogen. And then I have a carbon here, a carbon here, and a carbon here. Okay, let's see what we got. So for step 1, the first step of trying to decide what priority this stereocenter has, this is the stereocenter, of course, right? What I'm referring to as out is the wedged out group. So what do we have at wedged out? We have a carbon on the first step. What is dashed back on the first step? A hydrogen. And what is going up on the first step? This is up. So this is out, up. So up, we have a carbon as well. And then right, that's a carbon as well. So we see we've got a three-way tie, and then the H is already decided. So, excuse me. I had a sneeze. So I have a three-way tie there. H is the lowest priority already, though. We know that already. So we're like, yep, done. H is D. Okay. And then now we have to go stepwise to the next step. So I'll go in a different color to make it more obvious. So as far as the out one goes, there's a carbon here, but you treat it like 3 carbons when it's a triple bond. So we have our red carbon, and then it's got 3 carbons attached to it because it's a triple bond. So it's step 2. I'm going to write this as carbon, carbon, carbon. Okay, and now the back one, it's already decided. I don't have to worry about that because the hydrogen already lost. And then up, what does up have attached to it? It has a hydrogen, and then we count it as 2 carbons, right? Because it's a double bond. So that one's carbon, carbon, hydrogen. The right one is got a hydrogen, and a carbon. So it's carbon, hydrogen, hydrogen. So I can already decide all the priorities because these 3 are different already. So what's the highest priority out of all these? The wedged out group, the up, or the right? It's the wedged out one because the carbon, the first carbon, it ties with the other's first carbon. Its second carbon ties with the up, but it already beat out the right. And its third carbon beats the up's hydrogen. So this is our highest priority, A. What's our second highest priority? The up or the right? Yeah, the up, the B, and the C. There we go. So I can add these on and assign RRS. So wedged out is the highest priority, A. Up is B. Trying to get in here. B. Down is C, to the right is C, and then back is D. So are we viewing it in the easy to assign way? Yes. And so we just draw an arc from A to B to C. Is that clockwise or counterclockwise? Clockwise. So this molecule stereocenter is R. We got it. Now, I said I'd show you tricks on these priorities. I think. Let me actually. I'm going to write out a sample problem like this one. Let's go. I'm writing this on my Jamboard, but I'll show it. I'll share it shortly. So on this one, do you see how this is a stereocenter? It's tetrahedral. It's got 4 different groups. And what's with the D? What's that D? Yeah, the D is deuterium. Or the H1 isotope, H2 isotope, I'm sorry. It's got the 1 proton plus 1 electron. I mean, 1 neutron. So when we rank priorities, we're supposed to say, okay, whoever's got the higher atomic number is the higher priority. But deuterium and the H1 isotope of hydrogen and the deuterium, the H2 isotopes, they have the same number of protons. They have the same atomic number. So who do you think should be higher priority? So if you have more neutrons, you're the higher priority. Hopefully that just seems to make sense, right? So it winds up for this one, the lowest priority is going to be the hydrogen dash back, which I'm giving the letter D as a priority. It's not deuterium. It's kind of gets confusing on these. I should probably use numbers for these, but I just haven't. And then this is C. And now between these next ones, I've got an oxygen with a bunch of really heavy iodines on them, and this phosphorus with just a couple little hydrogens. Who do you think is the higher priority out of those two? So when we make our prioritizations, stepwise, steepwise, has to be stepwise. That's the key. Let me make this bigger. Title. What I mean by that is we have to do this. We have to say, okay, first step, I've got an oxygen and a phosphorus. If they're not the same, I decide already. I don't keep going. So are oxygen and phosphorus the same? Nope. Oxygen has an atomic number of 8. Phosphorus has an atomic number of 15. Higher priority. It doesn't matter what happens after that. So imagine if you were friends with Kahn, Ingle, and Prelog when they were making up these rules, and you were trying to help make the rules up to where you can quickly assign RNS values. Would you want to make a rule where you said, okay, we're going to add up everything here. We're going to add up all these, say, atomic numbers, oxygen, carbon, iodide, iodide, iodide. We're going to do the math and we're going to compare it to adding up all the numbers here, phosphorus, hydrogen, hydrogen. Would you want to make that the rule? Or would you rather say, no, once they're different, let's forget about having to add up the rest of it. Let's just decide right then. That would be faster, right? So that's how it goes. So you don't keep looking, do it stepwise. Stop when you're there. So it turns out the phosphorus beats out the oxygen. It doesn't matter what happens after. So is our D facing away from us the way we like? It is. So it's easy. A, B, C, D. A, B, C, yeah. So is this R or S? Does that look, what does that look to you? Look clockwise or counterclockwise? Counterclockwise. This one's S. Okay. I'm going to end with one last one, and we're not going to be done with this chapter. We still got more to do. I'll show you these tricks next time. But I want to do one of my favorite questions with Stereochem that I always ask. I got this same question on my O.Chem exam way back when. So what the question is it asks you to draw out all stereoisomers of a certain structure. Draw. Let's make it like we'll do the butane. Yeah, we'll make it 2,3 dichloro butane. All right, so we're going to draw that out. First, I'll draw it out. This is slide 12, right? My iPad is kind of behind. I'm going to turn it off, turn it on real quick here. There we go. Now it's cut up. So what are we talking about here? We're talking about 1, 2, 2,3 dichlorobutane. Okay, so how many stereocenters does this molecule have? It has 2 stereocenters, one right there, one right there. Each of them are stereocenters because they have a chlorine and a hydrogen, a methyl, and then the big rest of it, 2 stereocenters, and there's a formula for this. If you write out 2 to the number of stereocenters, that equals your max number of stereoisomers. So for this one, it's 2 to the 2. There's 4 max. So what this is telling me is I could have 4 stereoisomers. I can't have 5, but since it's max, it means I could have less. It might be 3 instead of 4. So how do I like to approach this problem? I draw the molecule out with all combinations of wedge and dash. So for instance, I could have the first chlorine wedged and the second chlorine wedged. What's another combination for them? I could do both dashed, yep. It's another combination. One wedge, one dashed. It's not really called trans though. It's because the molecules can rotate. And then one more. Dash on the left. Wedge on the right. Okay. So that these may have, some of these might be duplicates. It's not necessarily true that these are all unique molecules. And when you do this kind of problem, I want you to like erase, cross out the duplicates. So how can I find duplicates? One way to help me find it is to determine Rns values, because if they're like, if I have a couple that are both like RR, then I'm like, oh, they're equivalent. or, you know, something like that. So let's look. So I'm going to do this one first. So do you see that this would be my highest priority, the chlorine A. And then this would be B. This would be C. And then the H is dashed back as D. And what is this, clockwise or counterclockwise? A, B, C. It's clockwise. So this one is A, B, C. This is R. On the other side, it's going to be A, B, C, and then the HD is back as well. So what does that one look like? A, B, C. Is that clockwise or counterclockwise? Clockwise as well, huh? So I've got an RR. Okay, so I'm going to teach you a trick, a superpower. But with great power comes great responsibility. You can only use this great power for good. And when I say that, I mean for getting the right answer. So be careful when you do it. This is the great power. If you switch any two groups of a stereo center, the Rns switch, so let me demonstrate that and then tell you why you have to be careful with it. So for instance, this left carbon, carbon 2, that's R over here. It has a dashed back hydrogen, correct? When I look at it over here, the hydrogen is now wedged and the chlorine is dashed. The methyl and this stayed the same. So I just switched any two groups. So what should that stereochemistry be? Absolute configuration, it should be S. That makes sense? So on the next stereo center, when the chlorine's wedged and the H is dashed, it's R. But when I switch the chlorine and the H, because now the H is wedged, it should be what? S as well. So why is it, do I say, with great power comes great responsibility? The reason why is if on your first one, if you make a mistake on this one, then you're just going to duplicate that mistake for every other one. So the great responsibility is get the first one right. Or correct. So because if you don't get the first one correct, then it's going to go and kill Uncle Ben at the bank robbery, and you could have done something about it. Now you got to live a life of crime, fighting, be in the Marvel movie where you disintegrate. Oh, it's tough. So don't make a mistake on the first one. So okay, let's continue then. Let's say the first one's not incorrect. It looks correct to me. ABC, ABC, yeah. Okay, so now this next one down here, bottom left, what should the stereo center on the right be? Yeah, the left one is going to be R still because it's the same. Nothing was changed. What about this one here? It's going to be the opposite. It's going to be S. And then what about this guy here? That one's S. And this one is R, because it's the same as the first one. Okay. So I'm trying to look for duplicates, see if any of these are exactly the same. So does it seem like these two are the same, the RR and the SS? They're not the same. If you have the exact same RRSS, then you're not the same. I mean, if you don't have exactly the same RRSS, you're I'm mixing myself up here. These are different. Okay, what about this one? I got one R, one S on both of those. They can be the same, maybe. That should get the spider senses tingling. They both have one R and one S. Are they the same? Turns out they are the same. If I take this one and I rotate it on the screen 180 degrees, it'll look like this. And do you see how that's the same as the original? The bottom two are not enantiomers. The bottom two are the exact same molecule. Enantiomers are different molecules. So these are the same. So we don't want to present them as the answer as if they're the same. I mean, as if they're different molecules. They're actually exactly the same molecules. And so now for my final answer, when I want to like state drawing all the isomers, unique isomers, and then say how they relate to each other, I'll do that on the next panel and we'll finish there. I like to draw these up geometrically. If I have 3 stereoisomers, I'll draw them in like a triangle, because then you can relate them all easily. If I have 4 stereoisomers, I'll draw them up in a square. 5. We're gonna go crazy, pentagon. I'll show you what I mean. In this case, I have 3, right? So that first one, let me see, I drew it like that, yeah. I had the wedge, correct? And that was a neat, unique one. And then the dash. And then the wedge dash. I only need to draw one of the wedge dash because they're both the same thing. And then I'll throw on my R and S's again. So let's see, A, B, C. This is the R. A, B, C, this is R. So this is R, S, S, S. Okay, how are these all related? These two wind up being enantiomers. They're mirror images, and they're not the same molecule. Non-superimposable mirror images. Maybe you could see it if you imagine like picking this one off the screen and holding it, hovering it over on top of this one. See how they're mirror images? And then these ones, so let me see, mirror images. Then these ones, are they mirror images? No, they're not mirror images. Even if you twist it around and try to get them to be mirror images, they're not. So these are then called diastereomers. And then these ones here, these two are also diastereomers because they're not mirror images either. And at first, it seems like, wow, how did he know that right away? But there's tricks to help you. Like if they are enantiomers, then all the R's have to switch to S's. If they're diastereomers, then you have some that are the same. See how these two R's are the same, and then some that are different. Whereas these are diastereomers too, because we got opposite and the same. And there's one last thing, which I'll just state now, but I'll go into later. This molecule is meso. Next time. So meso's it's not a pair of molecules you describe. Meso is just like, oh, that particular molecule is meso. It can be confusing sometimes because like enantiomers is comparing a pair, diastereomer is a pair. But this one molecule is called meso because it's achiral, actually. It doesn't rotate plane polarized light. And we'll go into that next time. All right, good job. We're getting there. Just need to keep practicing it. You'll get it. And this stuff that we're learning right now, the Stereochem, we're going to be using this for the rest of the semester and the rest of the year. It'll become like other things, hopefully becoming like bond line structures, just come background. So like after chapter 5, we'll do chapter 6, and its reaction undergoes a Stereochem change.